backwards and we're going to say, well, here are the zeros. What does the polynomial end up looking like? Okay, so we're just going to be working backwards of what we have been doing. So the first thing we have here is the fundamental theorem of algebra. The fundamental theorem of algebra states that every function defined by a polynomial of degree 1 or more, so pretty much all of them, has at least one complex zero. What does complex mean again? It's a complex number.
It's complex.
It is complex. What makes it complex? What does it look like? Yes, it ends up having an imaginary solution. So remember we had our complex numbers that look like this, a plus bi, where a is the real part, b is the imaginary part. Okay, so we should be checking to see if we have any complex solutions. And the way that we would notice that is if I get to a quadratic that I can't factor, then I'm going to have to either complete the square like we did in that one problem or use the quadratic formula to solve it out. So you have to think about all your different methods that we've used in the past. Kind of already been talking about this, the number of the zeros. So if your polynomial has degree n, then it has at most n distinct zeros. Remember I've been saying if it was a cubic polynomial, then you should end up with 3 linear factors, 3 zeros. If it's a quartic polynomial, then you should end up with 4 zeros. So the number of zeros theorem states that a function defined by a polynomial of degree n has at most n distinct zeros. So it's an easy way to check to make sure you're getting all of your zeros covered. So if you look at what the degree of that polynomial is, that's how many zeros you should end up with. Now with that being said, sometimes you end up getting a zero more than once. And that's called the multiplicity of that zero. So this might be a new word that you haven't heard before. When we say that something has a multiplicity, it's when a zero occurs more than once. So maybe in your graph, it may be a cubic polynomial, meaning the degree is 3, but if you graphed it, it may only have 2 x-intercepts. So maybe it's only crossing the x-axis twice. Well, if it's a degree of 3, that means it needs to have 3 zeros. So that means maybe there is one of those zeros occurring twice. And what would that look like? Well, if I had something like this as my factored form, what's my zero here? -2. My zero here is -2. My zero here is 3. Well, you don't need to write -2 twice. If you were to graph that, you wouldn't put 2 dots at -2. It would just be 1 dot and 1 dot at 3. But you do have 3 linear factors. So if you were to multiply this out, you would end up with x to the 3rd power. But you would only have 2 x-intercepts. That's because this one has a multiplicity of 2. It's occurring twice. Okay? All right, here we go. Let's do some math. So we're going to create a function that has the following zeros of -1, 2, and 4. And then what's going to happen is I'm going to stretch it or condense it. So when I evaluate the function for the value of 1, my output needs to end up being 3. So that means if I were to input 1 for x, the output should come out as 3. So let's first just focus on these zeros. How many zeros do you have? 3. So that means I should end up with a cubic polynomial. Now think backwards. If I have a 0 of -1, what would that look like in linear factored form? Good. So x plus 1. If I have a 0 of 2, that would be x minus 2. And if I had a 0 of 4, it would be x minus 4. That's the easy part. Okay? That's not very hard, right? If I didn't have this extra condition, then I would be done. Okay, we could multiply that out. hopefully, and then turn it into a cubic polynomial. But I need to figure out this condition first. So I need to think about, I'm going to have some multiplier a, that when I evaluate this function for 1, it ends up coming out as a 3. So now let's think about this for a second. That 1, does it represent an x or a y value? An x, right? And this then should be your y. So if I were to go and input a 1 in place of all my x's, these would turn into actual numbers, right? So that's not too bad. So let's do that. So I'm going to have a times 1 plus 1, 1 minus 2, 1 minus 4 needs to equal 3. Can we solve that equation for a? Sure. Work inside your parentheses. 1 plus 1 is 2. 1 minus 2 is negative 1. 1 minus negative 4, or sorry, 1 minus 4, I'm saying that wrong, is negative 3. When we multiply these all together, what do we get? Positive 6. So I get 6a is equal to 3. So what does my a need to equal? 1/2. Good. So now what I can do is I can go back up here, and now instead of a, I'm going to turn that into a 1/2. And then we have to do some multiplying. Can I erase these steps? Does everybody have that? Okay. So I have now 1/2 times x plus 1 times x minus 2 times x minus 4. Now me personally, I would save the 1/2 until the end and multiply all of my linear factors first. So let's focus on the first two. X times x would get us to x squared. Negative 2x plus x would be negative 1x. 1 and negative 2 makes negative 2. Now let's multiply that with the x minus 4. X squared and x is x to the third. X squared times negative 4 is negative 4x squared. Now I'll take the negative x to everything. Negative x times x is negative x squared. Negative x times negative 4 is positive 4x. Now distribute the negative 2 to x, negative 2x, plus 8. Combine like terms. So we end up with what? X to the third minus 5x squared plus 2x plus 8. Bless you. And then my last move would be to multiply everything by 1/2. So what does that get us? Let me quickly make sure that the book takes it all the way there. Do they take it? Yeah, they do. I was going to say, let's do less work if we need to. So 1/2 x to the third minus 5/2 x squared. Half of 2 is 1x. Half of 8 is 4. And then we just need to make it a function. So I'm going to make it f of x, since they gave us an f here. There it be. Okay. So it kind of makes sense that if we went from here to here, we would be using synthetic division. So to do the reverse, it does make sense that we should be doing multiplication to get to that. Okay? Questions with this type of problem? All right. So now we got to get to the conjugate world. Oh, do we need to do another one? Let me just set this up quickly. We won't do it. If you're told, guys, if you're told that you have a multiplicity of something, so negative 2 is a 0 with a multiplicity of 3, what would that look like in factored form? It would be x plus 2 how many times? 3, right? So if it has a multiplicity of 3, that means it's going to happen 3 times. And then we would just do the same thing. We would input Input -1 for x, solve for a, right? Yeah, no, don't do that. If it says that you have -2 is a 0 with a multiplicity of 3, that means you're going to write that factor out 3 times. Okay? I won't go through the actual steps. What? That's complicated?
No, I'm tired.
Oh.
It's so fucking gross.
All right. So, oops, I'll bring that back. Sorry. So now, back when we were talking about the conjugate, when we did that one problem where we had the -I and then we did the I for the second 0, if you end up getting some type of polynomial function that has a complex 0 as one of its 0, then it always holds true that its conjugate will also always be another 0. Which kind of is a pain because you're like, oh, now I got to deal with conjugates. But if you get one complex 0, you can easily get the second complex 0 by just thinking about the conjugate of it. So it kind of gets 2 of your zeros done pretty easily. So the conjugate zeros theorem says if f of x is a polynomial function having only real coefficients, and if a plus bi is a 0 of f of x, then a minus bi would also be a 0. So the conjugate zeros theorem states that if you have one complex 0, then the conjugate also is going to be a complex 0. So if positive I was one of your zeros, then negative I would also be one of your zeros. If 2 plus I was one of your zeros, then 2 minus I would be another 0. If 3 plus 2i was a 0, then 3 minus 2i would be a 0. So if you have anything that has an I in it, you need to wrap your brain around what is the conjugate of that, and that would also be one of your zeros. So if you're given one complex 0, pretty much you have 2 complex zeros right off the bat. Okay? All right, so let's do one with some complex zeros in it. All right, so here I'm giving you, your zeros are 3 and 2 plus I, right? A polynomial function.
So this would be a degree of 2.
Not necessarily, because remember, if you have an imaginary, a complex 0, then you have another one. You have its complex. So you always kind of have 2 together. So this would be 3. So I have a 0 of 3. We know what that looks like in a linear factor. What does that look like? Good. Now this is where it gets a little bit tricky. If 2 plus I is 0, then that also means that 2 minus I would also be a 0. Now what would those look like as factors? Bless you. Here I had a 0 of 3, so all I had to do was do x minus that number, which was 3, right? So what would the factor look like for 2 plus I? Yeah, so now we have to really quickly just watch this, because it really doesn't matter how you write it. If I were to put x minus 2 plus I, am I technically distributing this negative? Now don't write this, just watch, because it really doesn't matter. So technically it would be x minus 2 minus I, and then if you did it the other way around, it did x minus 2 minus I, what would that end up distributing to? It would be x minus 2 plus I. So you would still get these two things if you just did x minus, the 2. Does that make sense? But technically, you have to think about distributing, but you won't get it wrong if you just do x minus 2 plus I and x minus 2 minus I, because you're going to get there either way. It's just the opposite of them. Does that make sense? So, if we just do x minus each of them, so x minus 2 plus I don't want to make plus a t, plus I, and then x minus 2 minus I. They didn't give us any f of anything equals anything, so that's nice. So I don't have to do any of that a jazz. So now we need to multiply this out. My suggestion is to start with the complex ones so I can try to eliminate all of my i's. So what's that going to look like when we multiply? X times x, x squared, minus 2x, minus, yep, just ix, right? I'll take the negative 2 to everything. Plus 4, plus 2i. Good, I'm running out of space. Now I'll take the I to everything.
Plus ix minus 2i plus, no.
Minus I squared, right?
Wait, but then wouldn't that make it
Right.
-1?
Right, which would go to a, well, it'd be minus a negative 1, so that would technically be a plus 1. Combine like terms. Anything else combining with the x squared? How about how many x terms do you have? You have a negative 2x and a negative 2x, which makes negative 4x. What happens to your ix's?
Cancel.
What's going to be nice is everything with an I is going to cancel. What happens to your 2 i's?
Cancel.
So then you're left with a 4 and a 1, which makes 5.
That's nice.
What about the x minus 3? Where?
Well, we didn't multiply that yet. I just did the last two. So now I'm going to take that quadratic trinomial and multiply it with x minus 3. I'm going to erase this top part, side room. So multiplying that out gets you x to the third minus 4x squared plus 5x. Now take the negative 3 to everything. Negative 3x squared plus 12x minus 15. Combine like terms. X to the third. What's it going to be? Minus 7x squared. 17x minus 15. And let's call it f of x. There you have it. Okay. Can we stop with the immature noises? All right, questions with that?
Looks good.
All right, we got one more example. So this is kind of similar to that number 19 that I gave you guys for the homework. But we're going to have to go back and use synthetic division and think about the idea of the conjugate. So if I had the polynomial f of x equals x to the fourth minus 7x to the third plus 18x squared minus 22x plus 12, and they're giving us that 1 minus I is a 0, think about the conjugate. If 1 minus I is a 0, then what else is a 0?
1 plus I.
1 plus I. Because I'm starting out with a degree of 4, how many times do I need to do synthetic division
4 times.
to get to a quadratic? Twice, right? Do you have 2 of your zeros? Yes. So we're going to use those in our half boxes. So the first one let's use is 1 minus I. My coefficients are 1, negative 7, 18,
Someone dying.
negative 22, and 12. Bring down the 1. What's 1 times 1 minus I? 1 minus I. All right, so what do I get when I add those together? I get negative 6 minus I, right? Oh boy, what do we get when we multiply these together?
It'll be -5 because the negative aspirate.
I'm going to do a sidebar up here. Negative 1 minus I times negative 6 minus I gets us negative 6 minus I plus 6I plus I squared. I squared is negative 1. So we get negative 7 plus 5I. Yeah?
Get 11 plus 5.
So then we get 11 plus 5I. Okay, oh goodness, now we're going to multiply again. Sidebar up top. 11 plus 5I times 1 minus I. So we get 11. So let's just try to do it. So negative 11I plus 5I would be what? Negative 6I?
Yes.
And then we get a minus 5I squared,
C.
which would go to a plus 5.
Yes.
So 5 plus 11 makes 16 minus 6I. So adding this gets us what?
-6 minus 6I.
Negative 6 minus 6I. Okay, so now we got to multiply those two together.
You just say it's a 12. Wait, should we just, if we already know it's a 0, can we just say 12?
You think we could? It's going to be a 0, right? Does everybody see why Justin's saying that? We know it's a 0. Shouldn't this end up being 12?
Or -12?
So if we check it, negative 6, then we get a negative 6I, no, positive 6I and a negative 6I, right, which will go to 0. And then we get a positive 6I squared, which would go to negative 6, and a negative 6 makes negative 12, so it would just be 0. All right, let's do one more synthetic division with the I1 plus I. Bring down the 1. Now what's going to be nice is I already have I's here, so it might be less multiplying. So 1 plus I gets us what? Negative 5, good. Multiply negative 5 times 1 plus I. 5I. Adding that makes 6. Multiplying gets us 6 plus 6I, which gets us 0.
Nice.
So what's the quadratic that we're left with?
-5x plus 6.
Good. Can we factor that?
-3, -2.
So we get x squared minus 5x plus 6 equals 0, which goes to -3, -2. So my two real zeros are what? 3 and 2. So all of my zeros would be 1 plus or minus I, and then 3, and then 2.
Is that the hardest thing we're going to do this chapter?
Yes. Okay. Huh? Now let's think about this though. If you graphed this on your calculator, where would the x-intercepts be? 3 and 2. So couldn't we use the 3 and the 2 in synthetic division also?
Yep.
And then it would have gotten us to whatever 1 plus I times 1 minus I is. What is that? 1... Oh, hold on. What am I talking about? It's not that. It would be x minus all those, right? So it would be x minus 1 plus I, x minus 1 minus I. So what would that be? X squared. I don't know. It would have gotten you to a quadratic that you could have then completed the square and get to that and get both of them. All right, let's do some practice problems. Grab yourself a practice space.